Okay, today we will learn the next part of current transformer. Before going to today's lesson, we have to recapitulate that about what is ratio error and what is phase angle error. What is ratio error? This is basic the difference between transformation ratio and the trans ratio of CT. Transformation ratio is nothing but the ratio of rated primary current to the rated secondary current. Here we can see as the nominal ratio, and the turns ratio is the ratio of number of turns of secondary winding to the number of turns of primary winding. So if there is any difference between the transformation ratio and the turns ratio, or the nominal ratio and the actual ratio, that is known as the ratio error. And next is the phase angle error. We already know in our previous class, it is already discussed what is phase angle error. Here we just can recapitulate that phase angle error value is depending upon the magnetizing current and the reflected secondary current. That means from phasor diagram we can see the magnetizing current and the reflected secondary current, that is IM, and reflected secondary current, that is the 180-degree displacement of the secondary current. Now come for the operational characteristics. What is today's lesson? Operational characteristics of current transformer. So operational characteristics of current transformer, here first is the effect of change in burden on secondary current. The burden, that is the secondary load. Burden is connected with the CT secondary, that may include ammeter, wattmeter, current coils, relay coils, and so on. All this being connected in series and carry the same current through them. Now in a current transformer, since we know the current depends solely on the primary current and primary current is independent of the secondary burden. So an increment in the burden, that means an increment in the burden impedance, will not change the secondary current but will demand more voltage in the secondary terminals, that is the VS, secondary terminal voltage. This will increase volt ampere burden of the secondary. With more instruments in the secondary, a higher voltage is required to make the current flow through that circuit. In turn, it will draw more flux to flow through the core, and hence as a result a greater magnetizing current or magnetizing component of primary current will increase. So in our equation of phase angle error, we can see it is dependent upon the magnetizing component of current. So if burden is increasing, with the increment in burden, the secondary current, with the increment in burden, the magnetizing current, that is Im, will increase. As the increment of Im, the value of phase angle error also be increased. As from the equation of phase angle error, we can see that if all are constant, so the phase angle error will be directly proportional to Im, that is magnetizing component of current. So as burden will increase, magnetizing component will increase, value of magnetizing current will increase. As a result, phase angle error will be increased. And as we know, the ratio error is depending upon the difference between transformation ratio and the trans ratio. As a result, magnetizing component of current will increase. There will be change between the primary current and the reflected secondary current. That means there will be change between the transformation ratio and the trans ratio. As a result, the ratio error will increase. Now the thing is that as basically CT is connected with inductive load, as a result the secondary current lags the secondary voltage or lags the secondary EMF. So the sigma, that is the angle between the secondary current and the secondary voltage is positive. Thus, the value of the ratio error will be negative. So if the ratio error will increasing, that means increasing in negative value means decreasing in nature. So with the increment in burden, ratio error will be increased, but as the CT is introduced or is connected basically with the inductive load, so the value of the ratio error will be negative. So increment in negative means basically nature of the curve will be decreasing. That's why we will get this. Next, the effect of change in power factor of the secondary burden. As it can be observed from the phasor diagram, here is our phasor diagram where we can see that the secondary winding current IS lags behind the secondary induced voltage ES. So first of all, power factor means either its power factor will be leading or lagging. So leading or lagging means it is inductive. Here the phasor diagram that we are seeing, this is for lagging power factor. For lagging power factor, we can see the secondary current will lag the secondary induced voltage ES. So the phase difference, that is this sigma, that phase difference is positive. Under this condition, the actual transformation ratio Under this condition, the actual transformation ratio is always greater than the trans ratio, and thus, as a result, always ratio error will be negative for lagging power factor. So, when it is lagging in nature, this will be positive. If this will be positive, so transformation ratio is always greater than the trans ratio. So the difference will be in negative. So the ratio error will always be negative for lagging power factor. And if it is leading, that means it is capacitive burden, then the secondary winding current will lead the secondary induced voltage ES. As a result, transformation ratio will may be less than the trans ratio, and then as a result, ratio error may thus become positive. The value will be in decreasing in nature, but the nature will be in decreasing nature, but the value, that is the amplitude that of for capacitive circuit, that is the leading circuit, that is positive, and for lagging this will be negative. So as the ratio error will increase in its negative value, the nature will be in decrement. Next, effect of change in power factor due to phase angle error. Here we can see that for inductive burdens, the phase angle error remains positive till a certain low value of power factor is reached at highly inductive burden when the phase angle error crosses over the axis to turn negative. Here we can see for inductive power, the phase angle error remains positive till a certain value. It is positive till a certain value. After a certain value, phase angle error crosses over the axis. Here it will cross over the axis and turns negative. And variations of ratio and for capacitive burdens, however, the phase angle error always remaining positive. For capacitive nature, phase angle means Im by NIS. So for this reason, we have already seen capacitive value is dependent upon magnetizing component of current. If the load is capacitive in nature, so the value will be trans ratio will be greater than transformation ratio, and from there we will get that the value of phase angle error will remain positive for capacitive circuit or for leading circuit, and for lagging power factor circuit up to a certain value, that means for inductive circuit up to a certain value it will have positive value, and after crossing of load value it will go to negative portion. So this is about the effect of change in power factor of secondary burden, and this is the effect of secondary burden power factor variation of on CT phase angle error. Next, this is the effect of change in primary winding current. As the primary winding current IP that changes, the secondary winding current also changes proportionally. With lower value of primary current, the magnetizing and loss components of no load current became comparatively higher. That means when value of primary current is lower, as a result, when primary current value is lower, then the no load components, that means the loss component and the magnetizing component of no load current became comparatively higher. As a result, if magnetizing component will be higher, phase angle error will be higher, as phase angle error directly proportional to magnetizing component. And if magnetizing component will be higher, so the turns ratio will differ from the transformation ratio. When no load component or the magnetizing component and core loss component will change, then there will be difference between turns ratio and transformation ratio. As a result, ratio error will be increased. So if the primary current decreases, here we can see if the primary current decreases with the decrement in primary current, the magnetizing current will be high. As a result, phase angle error will be high. Again, vice versa, if the primary current increases with respect to time, so magnetizing component will be decreases. As magnetizing component will be decreases, phase angle will be decreases. Look, primary current is decreasing in nature. Primary current is increasing in nature. As primary current is increasing, magnetizing current proportionately decreasing in nature. When magnetizing current will decrease, phase angle error will also decrease. So increment in primary current, phase angle error will be decreased. But when primary current will increase, so IP will increase. If IP will increase, there will be difference between IP and NIS, that is there will be deviation from primary current to reflected secondary current. If it will change, there will be change between transformation ratio and the turns ratio. So as primary current will increase, difference between transformation ratio and turns ratio will increase. As a result, ratio error will be increased. So here we can see with the increment in primary current, ratio error will also be increased. First, it will increase at a higher rate. After a certain value, its increment rate will decrease, but still it will increase. Those are the effects and those are the operational characteristics of current transformer. Next, there are some precautions for using current transformers. The first and important and foremost precaution is we have to avoid the open circuiting of CT secondary, which is very much important. Open circuiting of CT secondary. Current transformers are always used with its secondary circuit closed through very low resistance loads. Very low resistance loads. In such a case, a current transformer should never have its secondary terminals open circuited while the primary circuit is still energized. Under normal operating conditions, the secondary current produces a back EMF, so-called back EMF, that almost balances the primary winding ampere turns and restricts the flux in the core. This small EMF is responsible for producing flux in the core and supplies the iron losses. This resultant flux being small, the voltage induced in the secondary winding is also low. If by any reason the secondary winding gets open circuited, then the secondary reverse MMF vanishes. The demagnetizing effect of the secondary MMF is now absent, and the core then carries the high flux that is already created due to the primary ampere turns only. This large flux greatly increases flux density in the core and pushes it towards saturation. This large flux links with the large number of secondary turns, produces a very high voltage, and that could damage the winding insulation, as well as it can be dangerous for the operator also. So as a result, moreover, we can see the high magnetizing forces acting on the core, while secondary conditions tend to magnetize the magnetic material to high values. If the open circuit condition is suddenly removed, the accuracy of the CT may be seriously impaired by the residual magnetism remaining in the core. So for a CT, it is very much sensible thing to not to open circuit the CT secondary. For this reason, care must be taken to ensure that even when not in use for measurement purpose, the secondary circuit is closed at any time when the primary is energized. Next, permanent magnetization of the core. The core material of a CT may undergo permanent magnetization due to one or more of the following reasons. As already discussed earlier, if by any chance the secondary winding is open circuited with the primary winding still energized, then the large flux will tend to magnetize the core, and in such a condition, abruptly if it is removed, then there is a good possibility that residual magnetism will remain in the core. A switching transient passing through the CT primary may leave behind appreciable amount of residual magnetism. Permanent magnetization may result from flow of DC current through either of the winding. The DC current may be flown through the winding for checking resistance or checking polarity. The presence of permanent magnetization in the core may alter the permeability of the material, resulting in the loss of calibration, and it can increase in both ratio error and phase angle error. So, for reliable operations of CT, the residual magnetism must be removed and the CT be stored back to its original condition. And there are several methods for demagnetization that are going on. Those are all about the important topics of current transformer. Here we can see mathematical problems regarding current transformer. You all are asked and requested to go through the mathematical sections, and if you have any doubt, please contact. So in this, it is given that a 1500 5 ampere, 1500/5, that means primary current 1500 ampere, secondary 5 ampere, 50 Hz single turn primary type CT has a secondary burden comprising of a pure resistance of 1.5 ohm. Now we have to calculate the flux in the core, ratio error and phase angle error. As we have to find out the value of ratio error and phase angle error, that's why we have to just gone through that phasor diagram. For this phasor diagram here, it is given that this circuit is purely resistive circuit. If it's purely resistive circuit, the secondary current will not be leading or lagging. It will be 90-degree displaced, and so there will be no angle difference between secondary voltage and secondary current. Secondary induced EMF and secondary current will be in same phase, as the circuit is purely resistive circuit. So this will be our phasor diagram, that is flux in reference. This is the magnetizing current component that is in same phase, and with this this is IC, that is the core component, that is 90-degree displaced from the magnetizing component, and from there we will get the resultant value, that is the no load current. Again, as this is the purely resistive circuit, the secondary current that will be in 90-degree displaced from the flux, 90-degree displaced from the flux, and as a result we have to find out the values. We have to find out the ratio error as well as phase angle error. We all know the value of ratio error, that is the nominal ratio minus the actual ratio. Nominal ratio that we have to find out from the ratio of primary current to the secondary current. So, and here it is given in our question, iron loss is 3 watt. From that loss component of current we can find out, that is iron loss divided by primary induced voltage, and from that we will get the magnetizing component, that is magnetizing MMF, that is also given in the question, divided by the primary number of turns. As this is purely resistive circuit, so sigma, that is angle between IS and ES, that is 0. From there we will get the transformation ratio, and from there, and we know the secondary turns and primary turns. From there we will get the R. From there we will get the percentage ratio error, as well as sigma is 0. We came to know the value of IM, IC and IS, that is magnetizing current, core component of current, and secondary current. We will get the value of phase angle error. Next mass, that is a bar type CT with turns ratio this, and the magnetizing core component of primary current this, with rated condition determine the ratio and phase angle error for the rated burden. So here this is the effect of power factor. Here we can see what is given, turns ratio, we know NS and NP. From there this is turns ratio 1:199. From there we will get turns ratio value as secondary number of turns 199. Now we have to find out the nominal ratio value. This is turns ratio, this is the nominal ratio or the transformation ratio. This is our nominal ratio Kn or the transformation ratio. Loss component of current IC is 10 ampere, magnetizing component given 15 ampere. Now if the power factor is 0.8, for that 0.8 lagging, from that we will get the transformation ratio value. This is transformation ratio value, that power factor 0.8 means cos sigma is 0.8. From there we will get sin sigma. From there we will get sin sigma, and from there we will get the value of transformation ratio, that is R, that is the value of transformation ratio. Now ratio error, we already know the value of Kn, and this is our actual ratio, and from there we will get the ratio error, and from the ratio error we will get the value of phase angle error. Phase angle error value, that is depending upon cos sigma, sin sigma, as well as Ia and In, right? And from there again for 0.8 leading, as that was 0.8 lagging, that was for lagging power factor. Now for leading power factor, the value will be changed a little bit. From there we will get the value of transformation ratio and ratio error and phase angle error. You try it yourself. If you face any problem regarding that, please contact with me. Thank you.